So I will give this quick lecture about the Spelethem growth. And so basically, wow, why it's not moving? Okay, so the main points of this lecture is we first go quickly about the main factors that control Spelethem growth rate. Basically, the theories of Spelethem growth, and then the whole play by the main parameters that drive these Spelethem growth, that is calcium concentration, cave PCO2, temperature, dripping rate, and we go through quickly through some studies that could show us the potential application in paleoclimate studies, because actually when you're talking about Spelethem growth, it's all about the reconstruction of the hydroclimate variability. So let's go start. Well, factors that limit precipitation rate. If you consider the first assessment that was performed based on experiments, a very controlled experiment on lab with a constant dripping rate and on a solution with equilibrium and saturated in respect to calcite, we have the major factors that limit the precipitation rate are almost diffusion process related to the diffusion of CO2 molecular within the solution, the diffusion of calcium and carbonate within the solution, the position of calcium carbonate at the solid surface, and the production of CO2 at the solid surface. Well, among these four parameters, one of the parameters that's really important to us right now that really drive kinetic variations is the production of CO2 at the solid surface. That is really rate determining, because it determines also the kinetic of CO2 as the carbonic. As we know, the precipitation of calcite, we have this CO2 plus water giving carbonic acid, then carbonic acid, it 2CO3, it dissociate in one hydrogen and one hydrogen carbonate that then will dissolve the calcite. So, and this reaction is really rate determining. And well, we can put this in terms of a simple equation when the growth rate will depend on a kinetic factor and the variation between the calcium concentration of the solution with the calcium concentration at the equilibrium. So the difference between the calcium concentration of the solution when the solution is saturated in calcite, basically that. And this kinetic constant depends on temperature and also is calculated in terms of different concentration of CO2. Because just the cave PCO2 levels are also an important factor as they control the diffusion gradient across the water film. But then we can so simplify the main parameters that drive the calcite deposition rate as the variation of calcium, the concentration of cave CO2 atmosphere, temperature, and the water supply. So let's go through these main parameters. So first, the whole plate by calcium. As you see, the deposition rate of calcite could be simplified in this equation when you have a kinetic constant and the difference between the concentration of the calcium, the solution in respect to the saturation state. And basically, this rate will be dependent on temperature because the kinetic constant depends on temperature. And we have this theoretical prediction when we see the variation, the dripping rate, the deposition rate varies in function of the calcium concentration for different temperature. We also see that actually variations in temperature, these are variations and different variations in temperatures are, no, sorry, this is for only a single temperature. This is in different, this is in respect to difference of water supply of water thickness. So then you can see there's a linear relationship between calcium and deposition rate. But then we can test this experimentally. And the best way to test this is going through experiment in the caves using artificial substrate like that. Well, experiments like that has been performed since the mid-90s. And the use of this artificial substrate is really interesting, particularly this glass watch substrate, because it's curved, and also we can reproduce effect of the water flow across the borders. And this is particularly interesting because many effects like ray light distillation effect, when you're studying isotopes, fractionation factor, is also happen here. Like if you see the isotope concentration of carbon and oxygen across this water substrate, we see isotope enrichment across the border. So it really reproduces what occurs in the surface of Spelethem. So then, when we compare experiments that measuring the measuring the amount and monitoring the amount of calcite deposition through the replace of the substrate, we see there's a good relationship between variation of calcium and the deposition rate. This experiment that I've been performing in a cave in the last 80 years, when you see in black variation in deposition rate following the increase in calcium. And also there's this experiment that was performed by Baker in 1998. Actually, he combined a group of monitoring experiment of calcite deposition in 3 different caves in England, in France, and Belgium. And then we compared the deposition rate in respect to the amount of calcium for different caves, and we see a quite good comparison between the monitoring, the measuring deposition rate with the predicted in the theory. But then, apart from the amount of calcium, there's also the degassing, and the degassing is critical. It's critical, and most of the time is responsible for many seasonal variations in the deposition of calcite. And we can see this also in this experiment. Well, the degassing, as I showed previously, it has 2 steps, 2 major reactions. The equilibration between CO2 and water to produce carbonic acid, and then the dissociation of carbonic acid to produce hydrogen, a proton, and carbonic acid. Well, this part of the reaction, it's quite slow, but it's not that slow. Take just 12 seconds. However, this part of the reaction, this step, it's freaking fast. It takes just less than 1 millisecond to complete. So in general, the equilibration in the solution, the equilibration process between water and CO2 is quite fast. So the production of hydrogen carbonate is fast, which means that when the water appears in the tip of stalactite, the degassing process starts and completely and in a matter of minutes, I would say. But there's another important aspect of the degassing that we should pay attention. It's not just the fact that it's fast, but also there's a stoichiometric relationship between the amount of CO2 degassing and the amount of calcite precipitated. Look, this is the global reaction of calcite precipitation. Calcium and hydrogen carbonate, producing calcium carbonate, and then the degassing. So the global reaction is this. And if you pay attention, for every mole of calcium precipitate, I have a mole of CO2, which means that the amount of calcium carbonate that could be precipitated, it depends on the amount of CO2 degassed, which means that if the CO2 concentration of the cave atmosphere is high, so imagine a high PCO2, so the gradient between the solution and the atmosphere is low because there's also a lot of CO2 here. So there's a small amount of CO2 that could be degassed. So just a part of the calcium could be used to precipitate calcium carbonate, which means that the gradient of CO2 between solution and calcium carbonate, or in other words, the degassing controls how much calcium could be used to precipitate calcium carbonate. We can also see this in this is the classical curve of calcite precipitation. We have the amount of calcium. This is the curve of calcite saturation. And here the amount of carbonic acid that you can also take as the amount of KFPCO2 if you prefer, or in other words, the CO2 in equilibrium with the solution. So imagine a concentration that is pretty common to see in caves, like 2 micromole or 3 micromole per liter. And then if the CO2 of the atmosphere decrease, so the composition moves to here, and we have precipitation of calcite. So the gas in place a really important role. And you can see these also in the monitoring experiment. So this is a result of the monitoring experiment that I've been conducting. And in red, we have the curve of calcite deposition, milligrams per day of calcium carbonate deposition. And in blue, the concentration of CO2 in the cave. I just invert the axis. So here we have high CO2, and here we have low CO2. So when CO2 of the cave atmosphere is low, we have an increasing in the rate of calcite precipitation, and when the CO2 increases, the deposition rate decrease. So, and you can think and about the calcium. So if we plot the comparison of calcium, we see clearly that indeed what is controlling, what is driving variation of calcite deposition is the CO2 and not necessarily the amount of calcium. So where the cave CO2 came from? Actually, when you compare variation in CO2 of the cave with the temperature, there's always a good match. So when it's because the temperature outside the cave controls cave ventilation. So we know exactly how CO2 decreases in the cave. Basically, when it gets colder outside, the air gets more dense and enters in the cave. But how caves increase in CO2? Well, basically it increase through soil CO2 production. And we can measure easily using a camera like that. And this happened in temperate climate, but also we can see this happen in savanna climate. Like this is a savanna area in the central Brazil, and this is how it looks like during the dry season, during the winter, that's in June, July, and this is how the landscape looks like during the summer. Very different, huh? And if you monitor the CO2 of the soil, here we have like 4 points monitoring soil CO2. We see, and in the gray bar, variation of precipitation, we see that variation in precipitation drives soil vegetation, soil biological activity, and for consequence, the CO2 production of the soil, and then in the cave. So then when we compare the measured rate of CO2 in the soil and in blue, and we compare with cave CO2, we see that they goes hand in hand. At least the seasonal variation, why caves fill up with CO2, basically is a response of the soil. And in the tropic, this is more driven by precipitation. In temperate climate, this is driven by temperature, but then we have a control. We see that the CO2 concentration of the cave is driven by environment process outside the cave that then drive variations in calcite precipitation. As we see here, in the same kind of experiment, variations in the deposition of the Spelethem on blue, and on red, variations in the cave CO2. And we see that the seasonal pulsing, the interannual variability of CO2, of calcite deposition, is driven by variation of CO2. Of course, the amount of calcium also depends on the amount of calcite will also depend on the amount of calcium of the solution. But when we match these two circumstances, high concentration of calcium and low KFPCO2, we have high peaks of calcium. And we can see that the whole of the degassing also in Spelethem. This is one of my favorite studies about variations of PCP and KPCO2 drive variations in calcite precipitation in Spelethem. This is from Ronnie Boch from Katerloch Cave in Austria. And looking through these Spelethem, we see two different crystal fabrics. So this is a Spelethem with annual lamination. You can see this is our annual laminas. And basically there's at least 4 different types of annual lamina. Annual lamina could be petrographic lamina when we have difference between crystal fabrics. Could be rise in variation of mineralogy between calcite and aragonite. Could rise in respect to variation in organic material, or could rise in function of variation in trace elements. When you do not see the lamination in the naked eyes, but you see the variation peaks just in terms of trace elements. But well, this is an example of petrographic lamination when this annual lamina occurs in reason of different of crystal fabrics, and we have basically 2 crystal fabric, white porous lamina that provides a high vertical growth with column calcite, and a thinner translucent dense lamina. And the thinner translucent dense lamina occurs during the winter, while this porous fibrous lamina of calcite occurs during the summer. And what changes between summer and winter in this cave? Well, during the summer, actually this is inverted here, but anyway, during the summer we have a high KFPCO2 because the ventilation is reduced and there's more organic production in the soil. With high KFPCO2, we have low degassing. The pH of the solution, it's lower with more hydrogen carbonate. Dripping rates are higher because it's melted, and saturation index, it's lower, and forms this incomplete lateral coalescence of crystal that provide these fibrolaminas. While during the winter, we have a low KFPCO2, and this has happened because the temperature outside the caves it's lower, and then the air is more dense and pushed to an entrance in the cave, enhancing cave ventilations. pH of the solution increases, dripping rate also decreases because part is partially melted, the soil, and the saturation index also increases. And then we form this compact, dense calcite with increased lateral coalescence of the crystals. We can see the effect of the degassing affecting the isotopes. There's more degassing, so the delta 13 and delta 18O will be high in these layers that happens in the winter. Well, this is the result of the monitoring, but anyway, we see this pulses of CO2. See these pulses of CO2 drive annual variations. Well, there's plenty of other studies. This is another study showing annual lamina using, this is a petrographic lamination that is based on variation in the fabric of aragonite. All these layers are made of aragonite. And basically we have laminas, the white laminas, the thicker laminas that also precipitate during the winter when KFPCO2 it's lower, and then there more degassing. Does not mean necessarily the kinetic of the reaction is higher. Actually, when the gradient is higher, theoretically will be a higher kinetic of the precipitation, but the point is the amount of calcium that precipitate it's higher because the gradient between there's more calcium that could be used to precipitate calcite because there's more CO2 go away. Basically, is that. So the main period of calcite precipitation, again, is during the winter when precipitates this compact aragonite fabric, and during the summer we have a high KpCO2, less degassing, and we have these narrow and porous needle-shaped crystals of aragonite. And also, if you go through the monitoring data, we see something very similar, and monitoring also using this artificial substrate when we see peaks in precipitation of calcite here during periods of low KpCO2, and when KpCO2 is high, we have low precipitation rate, at least at seasonal time scale and interannual time scale. We see this variation of KpCO2 drive variation of calcite depositions. It's another study that goes in the same direction. We have annual laminas, and in this case, the annual lamina results from this precipitation of dark laminas here that occurs during the summer, and this is a kind of organic lamination. So the organic lamination is not a right name, but there's an example of lamination that caused by concentration of organic material that is usually well observed on ultraviolet and image, and we see again thick layers during the winter, and during the winter when KpCO2 again it's lower. As you see here, when the calcite deposition decrease, it's when KpCO2 is higher, and higher calcite deposition rate when CO2 also decrease again. So, and actually there's a lot of studies that show this effect of KpCO2 drive seasonal variations in calcite growth rate. And finally, we have the kinetic effect of temperature. And in theory, as temperature increases, we have also increases in calcite deposition rate. And this is because basically because the solubility of CO2 is fully dependent on temperature. If the temperature increases, the solubility of CO2 in the liquid decreases, as the same thing when you open a soda bottle. When it's warm, the degassing process of the CO2 is higher. So this control, there's an important kinetic effect, and also the amount of CO2 that is degassing of the solution. Well, and one of the interesting studies that shows this effect of temperature is this study performed by Banner and Richard in the caves of central Mexico. I really like this study, it's really well done. And we see he monitoring 7 monitoring points, and it's a cave, a well-ventilated cave. You see the CO2, it's nearly constant across these 3 years of monitoring. And we can see here variation of calcite growth. The author, well, he used a normalized curve that is the same kind of z-score data. And z-score data is when you have your data minus the average of the series divided by the standard deviation. So it's a way to remove the variance among the data, the relative variance among the data, and then you can compare all the different points and produce also a single curve of calcite precipitation. And in this case, as 35 Celsius degree, and during the winter, temperatures decreasing to near 5 Celsius degree. And on such amplitude of temperature variation, we see finally an important driver of calcite growth, a kind of condition that could match when we look to millennial scale variability of the last glacial, or when we compare temperature between glacial maximum and Holocene, stuff like that. And but the relationship between surface temperature and calcite deposition, it varies a lot. And also it's a function of the dripping rate. Usually fast dripping rate, we see a higher variation of temperature modulating a higher degree of dependence between calcite and temperature. And for slow dripping rate, this variation is not that high. And there's also interesting work that is recently published by Railsback, when he compared 80 different speleothems from the late Holocene over the last 3,000 years, comparing different of growth rate in those stalagmites and the local temperature. And because during the last 3,000 years, the mean annual temperature has not varied a lot. So we can do this kind of comparisons, and he collects Spelethem from different parts of the world, from South America, Europe, and Africa, and whatever. And he could see, well, we can see a reasonable agreement between annual temperature and stalagmite growth. Also, another aspect that could drive finally, so we have a calcium, CO2 temperature, is dripping rate. And in the sense that if you have fast dripping rate, we have more solution supply, we can precipitate more calcite. And we have also theoretical formulation for a relationship between water supply or dripping rate and precipitation of calcite, and also, of course, will yield different curves in function of temperature. However, this is not really works that well in most of the cases, because usually fast dripping rates most of the times are related to a large input of water, and many times fast dripping rates could be related to low saturation of calcite, which means a low concentration of calcium. So sometimes there's a not straightforward relationship between dripping rate and the saturation and precipitation of calcite. Of course, that this relationship tends to be better in dry climates, when you vary among conditions of a very limited amount of water and really rainy years. So in the same work, Railsback, he compares this relationship between the Spelethem growth rates from these different sites and the mean annual precipitation of the area. And a linear relationship tends to rise close here, but as we go through a very rainy areas, there is almost no relationship among them. So he also test this comparison when the author describes, well, possibly in dry climate, and what I'm gonna say, what are we gonna call as a dry climate is a climate like of a savanna area, when precipitation is less than 1,000 millimeters per year. We tend to see a positive relationship. It's not that good, but at least we see an increase in the growth rate as precipitation decreases. But for very rainy areas, this is not true. It's not possible to see, even in monitoring experiment, as in Spelethem's archive as a whole. However, as I said, the calcite precipitation, it's the relationship between dripping rate and Spelethem growth could work when growth rate is high, when a high in growth rate coincide with a favorable conditions of PCO2. So if these two parameters combine, like high dripping rate, low CO2, and high calcium concentration, then we see a good relationship between dripping rate and calcite precipitation. Like for this example, we have on black peaks of calcite deposition and dripping rate, and in blue. And we see there's not good match between peaks of calcite deposition and dripping rate. However, we see there's a good match between peaks of calcite deposition and cave PCO2. However, if you compare the relative variation, the relative annual variation between the amount of calcite precipitation and the dripping rate, they are in agreement. There's like a lag. Well, why this lag occurs? Because actually we need to look to that. There's a peak and there is a decreasing, but there's still a cup of water. The numbers of dripping per minute, it's like 8, 10 drippings per minute. So there's a good water supply at this time. And there's a reasonable water supply, and at the same time, a lower CO2. Of course, this is inverted, so we can precipitate the calcite. This is so similar that actually, if we just do a little lag in the deposition rate, you see a good fit between the between the annual variation of the dripping rate and the annual variation of calcite precipitated. I mean, the amount of water in the system. The point is, the peak do not occur together with the peak of the dripping rate, because the PCO2 at this time is still high in the cave, and in this time when the cave PCO2 decreases, then there's more calcite being precipitated. I don't know if I've been really clear, but anyway. And well, another problem, however, is that actually the annual variation of the dripping do not present a good linear relationship with annual variation in precipitation, because there's a lot of complex interaction, complex mixing in the karst system. So interannual variation of the dripping rate sometimes do not match the dripping variation, the interannual variation in precipitation. Like this is a study performed in a cave using 4 different dripping points. And this is annual variation in this blue bar. And we see that sometimes we have a raining year is also a high dripping rate among the 4 monitoring sites. But sometimes we have also raining years with small calcite precipitation. So the problem is the dripping rate sometimes do not follow a straightforward relationship with the interannual variability of precipitation in reason of the complex process that take places in the epicast and the karst reservoir. However, at the long time scales, they are more related. I would say. So in Brazil, the process governing stalagmite growth rate will be flux of water, dripping rate, the cave CO2, and the temperature. And then we can go quickly through some applications in paleoclimate growth, and go quickly through some climate, through some examples. And well, studies exploring the relationship between Spelethem dripping rate, Spelethem growth rate, and paleoclimate reconstruction are just, well, basically this is not well explored in the literature as a whole. I bring some examples. This is one of the oldest examples that I found. When we see from a cave in Tasmania, we see that variation in the Spelethem growth here match with variations in lake level of the surrounding area. And also, if you go through the proxies, we see like delta 18O, it decreases just a little bit during this period. So we have here a quite interesting comparison between growth rate and variations in the hydrologic regime. There's also a study that explored this relationship at the Levante, at the area of the Levante here in the Lebanon, where we see peaks of calcite deposition during the warmer areas, the warming periods of the last interglacial, So here we have peaks in calcite deposition related to variation of surface temperatures. We have some other studies exploring fast dripping rate, fast growth rate during periods of isotope negative excursions, like for this example in Africa, Spelethems, pulses of high Spelethem growth that matches with negative excursion in oxygen isotopes, and also with, this is very interesting, a part of the growth rate with layer specific width. So the authors also, they measure the layer width. And this is quite interesting because you have here a physical aspect of the Spelethem that is related to the this hydroclimate variability. This is another example from cave in Central Eastern Brazil. This cave is from the Holocene. The delta 18O is inverted, and we see during the Holocene. And during the Holocene, this is particularly interesting to be explored because during this period, at least temperature remains almost constant. So most of the variation of the Spelethem growth tends to be driven by variations in the hydrologic regime. And you see during the mid-Holocene, like pulses, large negative excursions of delta 18O here and here, that is also followed by a high deposition rate. But not just during the Holocene, this kind of study is also very interesting to be applied for very recent Spelethems. And particularly if you want to understand effects related to the global warming. So imagine, of course, the temperature variation during the last century, along the 20th century, the near 1.5 Celsius degree of increase in temperature that we've been going through in reason of the increases of greenhouse gas, is not enough to produce significant kinetic effect in the calcite deposition. However, there's many variations in the hydrological regime, no linear response of the hydrological regime in reason of this variation of temperature that can drive variations in calcite deposition. So this is a study of a Chinese Spelethem in the South China. We see a clear increase in the Spelethem growth rate along the 20th century that match variation of the Indian Ocean dipole mode. Well, this is a kind of no linear relationship between climate and atmosphere circulation, between temperature and the atmosphere circulation, that could drive variations in the Spelethem growth. And finally, I will show some quick examples of another experiment that we performed on a cave in Central Brazil. We have to publish this paper in this year. So this example of a well-ventilated cave in Central Brazil, the temperature here vary around between 25 and 50 Celsius degree, but the relative moisture also varies a lot, between 50 and 70%. So we use this well-ventilated cave sampling Spelethems here close to the cave entrance. So here we can see on blue variations in temperature of the cave, relative moisture of the cave, and in red variation in the relative moisture monitored in meteorological stations close to the cave. And we see that the atmosphere of the cave, it's in perfect equilibrium with the atmosphere outside of the cave. And we also see a comparison between dripping rate and calcite deposition. And what happened in this condition, we have the calcite deposition will be driven by variation of dripping, because we can assume that CO2 is nearly constant, and the water supply will be an important driver of calcite deposition, as we've been seeing in our monitoring. Here in red is the dripping, and in dark is the calcite deposition. And also evaporative effect will be will play an important role on that, because imagine a dry period where there's less dripping, but there's more evaporation. So then we collect spilethems from this particular site, and since there's a seasonal variation in the cave atmospheric conditions, temperature, and relative moisture, we also have this imprint in the spilethem as annual layers like that, and we have these dark layers, and also have a high imprint in the ultraviolet. That means that probably there's a lot of organic material here in these layers. But anyway, if we compare the growth rate here in black with the regional precipitation minus evapotranspiration potential, that is basically a function of temperature, or we can do even easier, even more simple. We can compare precipitation minus evaporation demand. Evaporation is measured in a meteorological station by a Pichet evaporimeter, but also you can use the temperature and convert in potential evapotranspiration using the Thornton-White equation. That it goes the same. So then we can compare the variation of calcite spilethem growth rate with the hydrologic balance precipitation minus evapotranspiration, and we see that they goes hand in hand along the 20th century. So as the climate is getting warmer, the evaporative demand is increasing, and the hydrologic balance is going towards more negative values, and we see the same stuff affecting spilethem growth. So I'm sorry, I pass a little bit, but that's it, guys. Thank you.